This presentation will look at the application of transcranial direct current stimulation in children with autism spectrum disorder. Autism spectrum disorder is a neurodevelopmental disorder characterized by restricted and repetitive behaviors, and people with ASD show deficits in social communication and interaction. It affects 1 to 2% of the population and is 4 times more common in males. People with ASD show frontal cortex development abnormalities leading to cortical underconnectivity. Specifically, the prefrontal cortex is an important region for social cognition, executive function, and emotional behaviors. And there's evidence for the impairments in this specific region as due to distributive networks and not a specific brain region. There's no cure for ASD, and interventions such as occupational therapy and pharmacological treatments have varying and limited success. Many people with ASD require lifelong support, so it's important to discover new treatment options. Transcranial direct current stimulation is an experimental treatment that applies direct electrical currents to stimulate specific parts of the cortical surface of the brain. It is mentioned as feeling like an itching or tingling sensation on the scalp, and it does not reach deeper brain regions below the cortical surface. A nodal stimulation excites neuronal activity by depolarizing the membranes, making an action potential more likely, whereas cathodal stimulation inhibits neuronal activity by hyperpolarizing the membrane and making an action potential less likely. As you can see on the right, the direction of the current flows from the anodal electrode to the cathodal electrode. Standard practice is generally around a 20-minute session at 1 to 2 milliamps, although this varies from study to study. Specifically, the dorsolateral prefrontal cortex is involved in higher order functions such as response inhibition, social cognition, and emotional regulation that is found to be impaired in children with ASD. Anodally stimulating the dorsolateral prefrontal cortex should therefore improve cortical functioning, particularly in the left hemisphere where hyperactivation, called rightward lateralization, is found in individuals with ASD. As you can see in Figure 2, targeting anodal stimulation of F3 or bilateral anodal stimulation of F3 and F4 is the most common target areas. Transcranial direct current stimulation can also modulate GABA and glutamate levels in the dorsolateral prefrontal cortex by lowering GABA levels and therefore lowering cortical inhibition. Children with ASD have also been found to have high levels of delta waves, and this treatment can increase alpha wave activity relative to delta wave. Experimental effects have mostly found that a nodal stimulation of the dorsolateral prefrontal cortex reduces measures of autism spectrum disorder. Most studies used around 20 sessions over the course of 3 weeks to a month with tests pre and post treatment. Macdonald and colleagues in 2014 found a significant decrease in the Childhood Autism Rating Scale and the Autism Treatment Evaluation Checklist, and Macdonald and colleagues in 2015 saw an increase in peak alpha frequency maintained for 24 hours relative to the sham condition, and a significant correlation between this measure and improvements in the ATEC in the social, health, and behavioural aspects. Both of these studies were randomized, double-blinded, and involved a sham condition, but were limited by a small sample size of 20 in each case, and a large number of tests run in each case increases the likelihood of a type 1 error. The size of the electrodes were also mentioned, meaning that it was likely that it generalized to areas bigger than just the dorsolateral prefrontal cortex. Toscano and colleagues saw measures of the Autism Behavioural Checklist and ATEC improve 1 week post-treatment with no change in the sham condition. Although this was a small sample of only 17, this was also found in 2 further studies, with the results persisting for up to 6 months. Unfortunately, these 2 studies included transcranial magnetic stimulation in children over 10, meaning we can't isolate the effects just to transcranial direct current stimulation. They also left out a sham condition, the importance of which can be seen in Q and colleagues studies, where they found no difference in reduction for ABC scores between the real and sham conditions. promising study of 43 participants found significant improvement in sociability, behaviour, health, and physical measures. They used bilateral and nodal stimulation over areas FC1 and FC2 with cathodal electrodes placed over the left and right supraorbital areas, as you can see in figure 3. This meant that electrical currents ran along the sagittal plane. Unfortunately, due to the different methodology, we can't draw on previous studies to add weight to these conclusions. It was also mentioned that the effect sizes were confounded by ongoing therapy being conducted throughout. All of these studies suffered from a generally small sample size, making it hard to draw conclusions and increasing the likelihood of type 1 errors. There is also a tendency not to publish negative results, meaning it's hard to determine the true effectiveness of this treatment without all results being published. The most pressing recommendation for future research is to establish more homogeneity between studies. The most recent meta-analyses could only include 3 studies due to differences in the methodology. Given the small sample sizes in this area of research, is it important to find common methodology between studies so research can build upon itself. More research can also go into the lasting effects of the treatment, looking 6 months and beyond, and given transcranial magnetic stimulation is shown to have a more significant effect and preferred in children over 10, transcranial direct current stimulation should focus its research in younger populations.